Okay, this second to last one on our paper is, let's get it in view. This is a pharmaceutical, and I think it's used as a blood thinner. You might know about this. Okay, come on. There we go. Getting the brightness up again. And so this should really be a textbook, as they say, for us now. This procedure should be really second nature. We put in the carbons where we know that they exist in this short form drawing. Line angle, representation, carbon, 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 and carbon. Okay. And we make sure that the carbon has 4 bonds everywhere, and here I have 3, so I'm going to add nitrogen, or hydrogens, not nitrogens. I'm going to add hydrogens where I need them. And careful, just, watch what you're doing, because here you could very easily keep going. 1, 2, 3, 4. Whoops, no. That carbon is fine. Don't do the oxygen, just carbon. He's fine. 2, 3, 4, he's fine. 1, 2, 3, 4, he's fine. This one needs a hydrogen. Whoops, sorry, camera. Oh, look, there's a carbon missing there. 1, 2, 3. 1, 2, 3. And that one already has 4. This one already has 4, but this guy needs... And I recognize that this carbon is fine because it's got 3 bonds plus another, so that's 4. Now, oxygen, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 2, 4, 6, 8, and 2, 4, 6, 8. Okay, so let's do the hybridization states of each carbon. Ready? sp2, 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 sp2. Let's do each atom we encounter, carbon or oxygen. sp3, sp2, sp2, sp2. The oxygen here, sp3. Over. sp3 carbon, because it's got 4 groups. sp3 carbon, sp2 carbon, sp3 carbon. sp2, sp2 all the way around the ring. Not central, not central. Bond angle here, COH. Central is the oxygen. We just said it was sp3, so its electron group geometry is tetrahedral, but its molecular geometry is bent. So this bond angle here is a little less than 109.5. I'm going to fix those. Bond angle, CCC in this conjugated ring, CCC, 120. Bond angle between HCH in the methyl pendant group. The C is the middle of a central to a tetrahedral, so any HCH bond here is 109.5. What is the molecular geometry around this carbon? Molecular geometry, same as its electron group geometry because it has no lone pairs. 1, 2, 3, 4. Tetrahedral. What's the molecular geometry around this carbon? Trigonoplanar. Are both of these rings in the same plane? Yes. And then it goes tetrahedral, but then this is another flat part. So all of these carbons are in the same plane, but all of these atoms are in the same plane. Okay, good. Last one is actually an ingredient in many sunscreens. And the sulfonic acid part down below here, this group here, makes it water soluble. And it's water soluble because once we add the electrons, you'll see how polar this is. It has a polar head to it, and the rest is kind of organic-y looking. Not much, except for the nitrogen. Okay, so let's, same thing, put in your carbons. It's our last one, folks. So be confident that you not only can do these examples, but have fun. Go look at a list of amino acids or artificial sweeteners, or I don't know, look at some of the steroid molecules. Anything that's predominantly carbon and hydrogen, but also includes nitrogen, oxygen, and sulfur. It's a huge array of molecules. And you can do this kind of analysis. And it's essential for you to be able to do that, for this course to serve you in further work. Whether you're going to look at active centers on proteins or drug interaction, or you'll look at making this stuff or using it or analyzing it or interpreting things. Whatever you do with it, it's really, really good foundation. And so it's not that if you see this molecule, then you're set and you'll be able to answer it, but be confident that you can do this on any of the molecules that are large organic molecules that employ polar covalent and covalent bonding. Okay? All right, all my carbons are in, and now I want to do make sure that each of them have 4 bonds. So 1, 2, 3, 4. 1, 2, 3. There's a hydrogen here. I'm trying to keep the paper flat, sorry, so it stays in focus. 1, 2, 3, 4, that's good. 1, 2, 3, 4 is fine. But each of my carbons here have a hydrogen on them, just not this one or this one. That has 4. This has a hydrogen, and this has a hydrogen. So now I'm going to look at the oxygen. 2, 4, so 6, 8. 2, 4, 6, 8. This oxygen also needs 2 pairs. And let's do the sulfur last. Let's look at this nitrogen. 2, 4, I know there's a bond here. 6, there's a lone pair. 8. 2, 4, 6, 8. I'll just remind you, back when we had our first look at organic acids and bases, we said that a base is a proton acceptor and an acid is a proton donor. And you'll do most of your acid-base chemistry in general chemistry too. But now that we're looking at a close look at the structure, do you see how a nitrogen with a lone pair is, I mean, I called it, I think, a landing pad for a proton, for an H plus to come in and land here, and here too, so that this molecule actually probably acts as a base in some environments because of the lone pair on an electronegative nitrogen. And so it could accept an H plus, and it could accept an H plus. So back here to the sulfur. The sulfur has 2, 4, 6, 8, 10, 12. Now, is that possible? Well, hopefully I won't give you a structure that's kind of a trick question like that. But let me just take you to the periodic table for a moment. And we said that once you hit atomic number 15, phosphorus, we know we're in the 3rd row of the periodic table, so the valence electrons are on that 3rd energy shell. We know there are s and p orbitals, but we also know there are d orbitals, which don't fill until I fill the 4s. So I have empty or vacant 3d orbitals up here, and I have empty or vacant 4d here and 5d and so on. So there's always d orbitals that are available, and so the argument is that with a nuclear charge that is part of a Z equals 15, or 15 protons in the nucleus, it can handle more than 8 electrons. It can actually hold on to them well. And so we will see, this is one of the exceptions to the Lewis structure rule of having an octet of electrons. So phosphorus can take 8 or 10 or 12. Sulfur can take 8 or 10 or 12. We often see, so anything 15 or greater can have 10 or 12 instead of 8. You will see in the examples phosphorus, arsenic, antimony, sulfur. Those are the ones that we'll see. So anyway, this is an example because on that sulfonic acid group here, I do have 2, 4, 6, 8, 10, 12. So that's fine. I'm just going to leave that alone. Okay? All right, so let's examine this for the electron group geometries. The electron group geometry, let's just go through. So I've got 1, 2, 3, and 4. So that's tetrahedral. 1, 2, 3, 4. What about that? How do I count that? I have 2, 4, 6, 8, 10. I have 12. But I count this as 1 and this as 1. So in terms of repulsion, they're actually structurally organized, these electron groups, as a tetrahedral. Over here, trigonal planar, same, trigonal planar, same. This nitrogen, 1, 2, 3, 4, tetrahedral. This carbon, trigonal planar. This nitrogen is what? It has 2, 4, 6, 8 electrons, but it has 1, 2, 3 electron pairs effective. And so this nitrogen is part of a trigonal planar. Interesting. That's a trigonal planar electron group geometry. This is a tetrahedral electron group geometry. This carbon, trigonal planar, the same as this one and the rest of them in this ring. So now, hybridization state, sp3. What about this one? What about that one? How many sigma bonds is it making? 1, 2, 3, 4. 4 sigmas, because only one of the lines in a double is a sigma, direct overlap. And hybrid orbitals can only be involved in making direct overlap. That's the whole premise for their formation, is that they hybridize the atomic orbitals that they have so that they can actually then point in the direction of the bond. So it has 4 sigma bonds, and then it's got 2 pi bonds. So S, 1, 2, 3. So it's actually using sp3, and then it's using other orbitals for the indirect overlap that create the 2 pi. Okay, so that one is tricky, but it's sp3 because atomic orbital or hybrid orbitals are used for sigma, and I've got 1, 2, 3, 4. Okay, hybridization state of this carbon, sp2, 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 sp2. This nitrogen is sp3. This one is sp2. This carbon is sp2. This nitrogen carbon nitrogen bond angle is 120. sp2, in fact the remaining are sp2. Now molecular geometry. Bent. What about this? Tetrahedral. This one, trigonal planar, all the same. This, the electron group geometry was tetrahedral, but one of those groups is a lone pair, so the molecular geometry is therefore not tetrahedral, but trigonal pyramid. This one, the electron group geometry is trigonal planar, but one of the electron groups is a lone pair, so then I'm just left with bent or V-shape molecular geometry. This molecular geometry is trigonal planar, the same as electron group geometry because there are no lone pairs. And that's the same as this one and the rest of them in the ring. They're all trigonal planar. So a few bond angles, HCC. Look at the central atom, determine that that's the middle of a trigonal planar geometry, so therefore this must be 120. Okay, good. So lots of practice.